Welcome to our video on the cardiovascular system, focusing on the heart and its functions. The heart is a crucial organ responsible for pumping blood throughout the body, ensuring that tissues receive oxygen and nutrients while removing waste products. Let's delve into the structure and function of the heart, as well as its conduction system and the cardiac cycle. The cardiovascular system comprises the heart, connected blood vessels, and the blood. The heart functions as a pump with two main halves. The right atrium and right ventricle receive deoxygenated blood from the body and send it into the pulmonary circuit. The left atrium and left ventricle receive oxygenated blood from the lungs and pump it throughout the body, which is known as the systemic circuit. Red blood cells carry oxygen, waste, and nutrients. Blood also carries immune cells and other functional cells that help maintain homeostasis. The pericardium is a thick membrane surrounding the heart, allowing it to beat without friction, expand, and resist excessive expansion. The parietal pericardium is the fibrous outer layer, while the pericardial cavity, filled with 5 to 30 milliliters of pericardial fluid, provides lubrication. The visceral pericardium, also known as the epicardium, is the thin, smooth inner layer covering the heart surface. The heart wall consists of three layers: the epicardium, outer layer; the myocardium, thick muscular layer with a fibrous skeleton; and the endocardium, smooth inner lining. The myocardium provides structural support and attachment for cardiac muscles and ensures coordinated contractions through its electrically non-conductive fibrous skeleton. The endocardium minimizes friction and prevents damage to erythrocytes. The heart has four chambers: the right and left atria, superior chambers receiving blood from the circuits, and the right and left ventricles, inferior chambers pumping blood to the circuits. Valves between the chambers control blood flow and prevent backflow. The atrioventricular valves are the tricuspid right and mitral left valves. The semilunar valves are located at the exits of the ventricles into the pulmonary and systemic circuits. Cardiac muscle, or myocardium, is striated and involuntary. Cardiac muscle cells, cardiomyocytes, are short, branched, and connected by intercalated discs. These discs provide tight mechanical joining via desmosomes and allow ion flow between cells through gap junctions, enabling synchronized contractions. Cardiomyocytes contain numerous mitochondria, actin, myosin filaments, titin proteins, and sarcolemma. The cardiac conduction system is myogenic, meaning the heartbeat originates within the heart. It is also autorhythmic, producing regular and spontaneous depolarizations. The sinoatrial SA node in the right atrium acts as the pacemaker, initiating the heartbeat and setting the heart rate. The atrioventricular AV node serves as the electrical gateway to the ventricles. The bundle of His transmits the signal from the AV node to the ventricles, and Purkinje fibers spread the signal throughout the ventricular myocardium. The conduction events in cardiomyocytes involve an action potential starting with depolarization. The SA node creates a stimulus that opens voltage-gated sodium ion channels, causing rapid depolarization. The action potential peaks at about 30 millivolts, then sodium channels close and calcium channels open, causing a plateau. Calcium ions prolong depolarization, leading to contraction. Calcium binds to troponin, displacing tropomyosin and exposing myosin binding sites on actin. The myosin heads perform a power stroke, pulling actin towards the sarcomere center, resulting in muscle contraction. Repolarization occurs as calcium channels close and potassium channels open, restoring the resting membrane potential. The refractory period in cardiomyocytes is longer than in skeletal muscle cells due to the plateau phase, preventing another action potential during this time. This ensures coordinated contractions and prevents tetany. The cardiac cycle has 5 major events: atrial systole, the SA node fires; atria depolarize, P wave on ECG, and contract, forcing remaining blood into the ventricles. Isovolumetric contraction, ventricles depolarize, QRS complex on ECG, contract, and the pressure closes the atrioventricular valves, S1 heart sound. No blood is ejected as all valves are closed. Ventricular ejection, ventricular pressure exceeds arterial pressure, semilunar valves open, and blood is ejected rapidly, followed by reduced ejection. Stroke volume is usually 70 milliliters at rest. Isovolumetric relaxation, ventricles repolarize, T wave on ECG, relax, semilunar valves close, S2 heart sound, and ventricles expand without filling. Ventricular filling. Rapid filling occurs as ventricular pressure drops below atrial pressure. Atrioventricular valves open and ventricles fill with blood. Heart sounds, S1 and S2, are generated by valve closures and can be recorded on a phonocardiogram. S3 and S4 are usually pathological in adults but may be heard in children or teenagers. The pressure volume diagram for the left ventricle shows the cardiac cycle stages: atrial systole, low pressure, high volume; isovolumetric contraction, rising pressure, high volume; ejection, high pressure, volume drop; isovolumetric relaxation, pressure drop, volume plateau; and diastasis, low stable pressure, increasing volume. The cardiac cycle duration is about 0.8 seconds, with more than half spent in diastole. Cardiac output, CO, is the amount of blood ejected by the ventricle per minute and is calculated as heart rate, HR, multiplied by stroke volume, SV. Normal CO is around 5 liters per minute. Myocardial function depends on preload, ventricular tension before contraction; afterload, arterial pressure opposing valve opening; and contractility, contraction force for given preload. Preload can be influenced by diuretics and saline solutions. Afterload impacts stroke volume inversely, and contractility depends on the inotropic state, myocardial fiber shortening. Positive inotropic agents increase contractility, while negative agents decrease it. During exercise, mechanisms such as proprioceptor signals and increased venous return elevate HR and SV, leading to higher CO. Regulation of cardiac function can be intrinsic, heterometric autoregulation, or extrinsic. Cardiac function curves show the relationship between right atrial pressure and CO, demonstrating that volume ejected matches venous return during steady state. Understanding these mechanisms is essential for diagnosing and managing cardiovascular conditions and optimizing heart function. Thank you for watching this comprehensive video on the cardiovascular system. Stay tuned for more in-depth explorations of heart physiology and medical diagnostics.